All right, so this video is to introduce you to the ratio and the root tests. These are two tests that we can apply to a variety of series to get sort of like a sharp, quick result for the convergence or divergence of these series. And in order to talk about the ratio test or root test meaningfully, we have to recall back from section 11.2, one of the facts that we saw about geometric series, geometric series are series that essentially each term takes the form of an exponential. So like r to the n here, for example, a sum from n equals 0 to infinity. Here r is just a constant. And from what we saw back in section 11.2, we saw that these series converge if r is less than 1 in absolute value, and these series diverge if r is greater than or equal to 1 in absolute value. In fact, we saw exactly what these converge to. They converge to 1 over 1 minus r, as convenient as that may be. But actually, we're not going to be too concerned about what the series evaluate to here. What we're simply going to be looking at is sort of the terms themselves. And in particular, I want to make two observations about the terms of our geometric series because there's sort of a particular property, or two particular properties, I guess, related to our geometric series that we can sort of exploit. So consider this ratio, if you would. The ratio of the n plus 1th term of our series divided by the nth term of our series. Well, if we were looking at a geometric series, the n plus 1th term would be r to the n plus 1, and the nth term would be r to the n. Now, what would you get whenever you divide those? Well, n of the powers of r downstairs would cancel with n of the powers of r upstairs, and what you would be left with is all of the powers of r canceling downstairs, 1 power of r remaining upstairs, and you would just get absolute value of r. So, note, for geometric series, when you make a ratio of an plus 1 over an, you get precisely the absolute value of r. And note how this is something that relates to the convergence of the series, because absolute value of r actually plays a key role in terms of the convergence of the series. When absolute value of r is less than 1, we get convergence, greater than or equal to 1, divergence. Right, another observation. What if we look at the terms of the series raised to the 1 over n power? Note, this is also, you could also write this, and we didn't here, but you could also write this as the nth root of an, right? Because the nth root here, how do you rewrite an nth root? You just write it as the 1 over n power. Well, what if you took each of the terms of your geometric series and raised them to the 1 over n power? Well, the nth term in your geometric series would be just r to the n, and if you raise that to the 1 over n power, well, power raised to a power, multiply the exponents. The exponent would just be 1. You would just have r to the 1, which is r. Well, specifically absolute value of r, I should say. Now, note, by the way, both of these expressions, taking the n plus 1th term divided by the nth term, or taking the nth term and raising it to the 1 over n power, both cases, you end up with absolute value of r, which is precisely the measure that determines whether or not your geometric series is convergent. And in fact, the ratio test and the root test are built off of these two observations. Note, in this first observation, you have a ratio of subsequent terms. In the second observation, you have a root of the nth term. And the ratio test essentially says this. If you have a series, so if you've got this thing that's a series, and you take a limit as n goes to infinity of the ratio of the terms, let's call that L. Well, if this L is less than 1, then essentially our series is acting like a geometric series with common ratio less than 1. So our series will converge. On the other hand, if when we take a limit as n goes to infinity of a ratio of subsequent terms with absolute values on them, if we get something bigger than 1, then our series is essentially acting like a geometric series with common ratio bigger than 1. As it turns out, as a result of using a limit here, there turns out being an inconclusive result in the boundary case of L equals 1. We'll get into more details about why that's the case in a moment, but what the ratio test says is if the expression, an plus 1 over an, absolute value, take that limit as n goes to infinity. If you get something less than 1, you are essentially acting like a convergent geometric series. If you have that ratio being greater than 1, you are acting like a divergent geometric series. If that ratio turns out to be 1, unfortunately the ratio test gives you no conclusive results. So be it. But that is ultimately the ratio test, and note this is built upon that ratio that we observed previously. What about the root test? What if you have a series, and what if the limit as n goes to infinity of the nth root of the absolute value of a term is equal to L? So you take an, absolute value, raised to the 1 over n power. Remember, this is like the nth root. We saw that previously. Well, we are going to get a similar result here to what we got with the ratio test. And that is to say that if this root as if this an term to the 1 over n taken as a limit as n goes to infinity, in other words, if this L is less than 1, then our series is acting like a convergent geometric series, and our series will converge as well. On the other hand, if this L, which is related to the terms of our series, if this L is greater than 1, then our series is acting like a divergent geometric series. On the other hand, if the limit turns out to be 1, unfortunately, this also is a result of the limit and some of the sort of theoretical sensitivities therein. We get an inconclusive result should L equal 1. But in both the cases of the ratio test and the root test, when we evaluate either this ratio or this root, if we get less than 1, we are corresponding to a geometric series with common ratio less than 1, which is convergent. On the other hand, if this ratio or this root evaluates as a limit to be greater than 1, then we are essentially corresponding to a geometric series where common ratio is greater than 1, and we will diverge. What about that L equals 1 case? I just want to hit this for a second so that we can see why we would get an inconclusive result. So why are we inconclusive in the L equals 1 case? Here's a classic example of such. Here's a pair of p-series. We have a p-series where p is 1. This is a divergent p-series because we know that p-series diverge precisely when the p is less than or equal to 1. Here we have a p-series with p equal 2. This is a convergent p-series because we know that p-series converge when p is greater than 1. Now what I'd like to do is take a look at the limits associated with the ratio test and the limits associated with the root test one by one for each of these series. So sum 1 over n is over here. Sum 1 over n squared over there. So we've got the two different series sifted through with the two different tests. Now, if you take the ratio of these 1 over n terms, you would get, let's see, 1 over n plus 1 over 1 over n. Now, that's a double-decker fraction, but if you keep change flip, you'll end up with n over n plus 1. Now, we're taking a limit as n goes to infinity, and we know how to deal with that because this is an equal heavy rational expression, same degree on top and bottom. Just look at the ratio of the leading coefficients. The ratio of the leading coefficients is 1 over 1, which is precisely 1. So here, the ratio test and the limit associated yields a value of 1. We're yielding a value of 1 here for a divergent series. What about the ratio test corresponding to the 1 over n squared series? Well, take the term a of n plus 1 over an. That would be, well, 1 over the quantity n plus 1 squared all over 1 over n squared. Now, this is also a double-decker fraction, but if you keep change flip, you'll end up with n squared over the quantity n plus 1 squared. Now now granted, we haven't FOILed out what's in the denominator. You could, of course, expand out n plus 1 times n plus 1. But what you would get at the end of the day would be a degree 2 expression for n, which is exactly the same degree as you have above. So this also is an equal heavy rational expression in terms of degree, and as a result, when you take the limit as n goes to infinity, you'll simply pluck off the leading coefficients. So here, 1 over 1 equals 1 as well. So here, we get into a situation where the ratio test and the limit associated yields a value of 1, but now we're yielding a value of 1 for a convergent series. So the key observation to make is the ratio test yielded a value of 1 in both of these cases, and in one case we diverge, and in the other case we converge. As a result, when we go back to the statement of the ratio test, note the ratio test is inconclusive at L equals 1. Well, if some L equals 1 series diverge and other L equals 1 series converge, we don't have a conclusive result in the case L equals 1. However, we do have a conclusive result if L is less than 1 or greater than 1, which is wonderful when such cases should occur. What about the root test? We could apply the root test to these two series, these two P series, which we know how the story plays out. So if you take the term and raise it to the 1 over n power, of course, 1 to the 1 over n power is just 1. Downstairs, we have the absolute value of n to the 1 over n power. This is a fact back from Calc 1, but this limit that's downstairs, a cheap way to remember this is it sort of starts to look like something to the 0 power, which something to the 0 power is 1. That's a cheap way to think about it, but it's ultimately what's going on. Long story short, this expression down here has a limit that is 1 via the root test. So that means our divergent series takes a value of 1 in the limit associated with the root test. Well, what about our convergent series? What will it approach? Well, actually, if we take the absolute value of an to the 1 over n power and write that out, apply the 1 over n power upstairs and downstairs. Of course, 1 to any power is 1. Oop, I need absolute values here. I've forgotten those around my n. So put the absolute value bars here. Well, the story plays out in a similar way because the power essentially approaches 0 as n goes to infinity, and if you have a number to the 0th power, you get 1. So a cheap way to remember that as well, here you get 1 for the root test. And so what does this mean? The limit associated with the root test is 1. Both for a divergent series and for a convergent series. And this is precisely why, let me bring back in this other slide. This is precisely why when we talk about the root test, we get an inconclusive result when our limit is associated with the root test is 1. Because here we get L equals 1 for a divergent series. Here we get L equals 1 for a convergent series. So there's no way to say whether or not we have a convergent or divergent series when L is 1. However, when L is less than 1 or greater than 1, we do get a conclusive result, which is a wonderful thing about the root test. Now, this limit that we brought up and we used in both of these cases here on the left and right to the 1 over n power, if that does not bring back great memories from Calc 1 and the argument that I made about the power approaching 0 you didn't really like, you could take a look at this slide. This slide contains some Math 160 review, and I'm not going to dwell on the details here, but it's essentially a walkthrough as to why the limit of n to the 1 over n power is equal to 1, and you can pause the video and check out the details and convince yourself if you weren't convinced already.